Hello, this is our ME-165 project presentation for the Mazda Miata rear brake revamp. My name is Daniel Cederberg,
My name is Brian Go.
And I'm Karash Sadr-Lashrafi.
and this is our presentation. Our objective. Our objectives are to redesign the rear brake system in order to reduce the heat generated through braking, reduce required force for stopping resistance to rotational motion, and reduce wear on the brake pads to reduce our operational costs. Original design modeling. The Mazda Miata rear braking system was a simple hydraulic caliper rotor system with a sliding caliper and a solid rotor. The problems with the original design is overheating. The rear pads would fail due to reaching excessive temperatures, which potentially endanger the driver, and the pads must be replaced frequently. You can clearly see that in the upper right side. These pads are completely worn out, and it was due to uneven applied pressure to the brake pads on the brake rotor. Yeah, uneven pad wear. Sliding calipers not distribute force amongst the pad evenly, as I said before, causes the pads and rotors to wear unevenly. Poor braking performances are due to this, and increased maintenance costs overall. And this car is not that cheap. This was our original CAD model of the original rear brake system. Over here we have the brake caliper, the knuckle, the wheel hub, and the wheel bearing, the rotor, and the brake pads. The main components that have been worked on are the rotor, the brake caliper, and the knuckle. Our improved design and modeling. Let's see, the improvements that we did was improvements on the caliper. We made it a fixed caliper with 4 pistons, which gives it a greater piston surface area, which is 5.5 times the original area. We also worked on the rotor. We made it larger and thicker diameter and dimensions, and we vaned it, as you can see here, to allow airflow. Two-piece aluminum hub with cast iron rod. So this part here is aluminum, and this part here is the cast iron rod. And the fundamentals that it increases are torsional resistance applied to the main axis here by the brakes. Because we have a greater surface area, we need to use less applied force onto the rotors, and cooling via convection. We hope to replace the caliper as well with aluminum, and we hope that the holes in here would allow for airflow, which will allow for convection cooling. In CAD, we redid the knuckle, the brake caliper, and we also redid the rotor with the drilled vane rotor. And this was done in 2 pieces, as we can see here. The benefits is vanes from the airflow convection for cooling, and the aluminum also for reduction in heat, and less force required for braking due to diameter torsion and torsional advantages. And this, when comparing, as you can see here, this is just, boring, plain, not that much surface area, no airflow. Over here, greater surface area. Again, we have greater airflow for convection.
So I'm going to go over the motion analysis. The overall goals were to assess and compare the braking performance between the original and the improved brake system designs. We used SolidWorks for our motion study, and our parameters were a rotational force acting upon the rotor of 60,000 Newton millimeters, and we used a clamping force using the cam feature and solid bodies. And for the sliding caliper, we had 100 newtons per pad, and for the fixed caliper, we had 550 newton per pad, because we now have 5.5 times the piston area compared to the sliding caliper, and in hydraulics, the area is proportional to the force applied at the same pressure. The friction coefficients we used in the simulation for the rotor was dry steel, and for the pads, we used dry rubber. And for our performance analysis, we used angular velocity plot in the angular velocity in the y-axis, and a lower rotational speed would indicate a better theoretical braking performance. I will review our motion analysis right here. As you can see, we have the torque applied to the rotor, and we have the force amongst the calipers, and we have our cam feature, which is the solid body contact between the rotor and the 2 pads. And if we run it at half the speed, it demonstrates our motion study, and shortly we'll be able to see the plot it produces. This is our plot right here. So if we compare the motion plots versus the original design, in our original design, the rotor was spinning up to almost 130,000 degrees per second, while on the improved design, it was only spinning up to 40,000 degrees per second, which is a substantial improvement over the original design. Now, for our finite element analysis, our goals were to evaluate and compare the thermal efficiency of the original and the improved model. Now for the study, we use ANSYS transient thermal study, and for parameters, we allocated materials, and we use cast iron for the rotor itself and aluminum for the hub and the caliper. We set an initial temperature of 22 degrees Celsius, which is approximate ambient. For heat flow, we did 200,000 watts acting upon the rotor. This is equivalent to the amount of stopping energy it would take to stop a 2,200 pound car from about 60 miles per hour. And for convection, we assumed 120 watts per meter squared acting upon all the cast iron surfaces. And for our performance analysis, we did a temperature plot, and a lower temperature would indicate better thermal performance. So we're going to review our ANSYS study, and this is our improved design. As you can see, we have convection applied across multiple components, and we have heat flow acting on the rotor faces. And as you can see on the temperature plot, we are seeing a maximum temperature of 850 degrees C. And we overall have very good thermal dissipation on the vanes of the rotor and the holes themselves. We can actually see here that the heat seems to be dissipating directly where the vanes are located. Now, if we compare the improved design charts versus the original design charts, as you can see, we have a maximum temperature of 850 degrees centigrade on our improved design, and a much higher 1,361 degrees centigrade on our original design. So as you can see, we have substantial improvements amongst the thermal performance of our braking system.
For our outcomes, we successfully created the rear brake system on the Mazda Miata and improved the design overall. We have increased the overall diameter of the rotor, providing a torsional advantage to the brake pads. We've made a new two-piece construction of the motor, made of aluminum and cast iron, made for better heat dissipation throughout the rotor. And we have drilled and slotted to increase airflow through the rotor, reducing the temperatures and increasing the heat flux. For our simulation conclusions, we ran motion analysis and finite element analysis. For our motion analysis, we have improved the mechanical performance by a factor of 3 and had less pad force required to meet the same level of torsional resistance. For the finite element analysis, we've improved the thermal performance by 45% and prevent brake pads from becoming more brittle, as well as reducing the cost from frequent pad replacements. For further improvements and recommendations, we have feature upgrades and performance enhancements. Some ideas we had were to reduce the number of drilled holes to preserve the structural integrity of the rotors. We thought about adding a cooling plate to direct more air to the rotors, and incorporating titanium shims to reduce the heat transfer between the brake pad and the caliper. Thank you for your time and listening to our presentation.